I think, can you see the?
Yes, it looks great. Yeah.
Okay. Hello, everyone. I'm Wende Xiao from Beijing Institute of Technology. Thank you for the invitation. Actually, Professor Yao was supposed to give this talk, but because of some reasons, he is not available today, and asked me to give this talk. So I will just do the job. Today, I will introduce Quasi-One-Dimensional topological material. This new family of topological materials has been a very hot topic. We just have seen that Professor Kondo have given a lot of interesting results. So I will introduce our recent work about this family and prospect its future. As we know, the quantum swing hole effect was firstly proposed in graphene by Kane and Belli. However, till now, only two quantum spin well systems can demonstrate quantum spin hole effect. It is well known that these quantum well systems are very difficult to prepare, and the working temperature is very, very low. So it is very important to search for new systems that can realize quantum spin hole effect at a high temperature. Although graphene was the first material proposed to exhibit quantum spin hole effect, but because the spin orbital coupling in graphene is very weak, so the band gap is only about 1 micron eV, so which is too small for any practical application or experimental observation. So in 2011, Professor Yao's group started silicon, which means use silicon atom to replace graphene, to replace carbon. And because silicon is much heavier than carbon, then the band gap is 1,000 times bigger. So this can be a quantum spin hole insulator. Along this direction, if we use even heavier atom, such as bismuth, then we can construct bismuth, which is also similar, which has also similar honeycomb lattice. So in this case, the band gap is about 1 eV. So this means this material might be possible to host a quantum spin hole edge state at room temperature. So
Wende, may I ask a question? So do you know what is the current status on the experimental side for silicon?
Yeah, silicon, there already has some experimental report about the preparation, but for any transport measurement is still not possible at the moment, because at the moment they usually prepare silicon on metal surface, so which means the topological edge state might interact with the substrate, and it's not possible to directly measure the transport property. But it's
so
also very difficult to transfer it to any insulating substrate. So this seems to be a very difficult work at the moment. Yeah.
So there, do you think that there are some chemical bonding between the metal substrate and the silicon?
I think so.
Okay.
I think because it seems to be rather difficult to remove this silicon layer from the metal substrate at the moment. So
okay, thanks.
The interface coupling seems to be rather strong.
Mm-hmm.
Yeah.
Okay, thanks.
Okay, let me continue. Then we also developed an effective method to calculate the Z2 invariance using first principle calculations. Our calculation is based on density functional theory, so I'm not going to tell you the details, but with this technique, we have predicted many systems to be three-dimensional TI. And furthermore, we also developed a dictionary of emergent particles and related softwares to calculate their symmetry and topology. So these are some papers. These are rather long papers. If you are interested, you can have a look at this paper. And we also made some softwares. If you are interested, you can also join the user group, and these softwares are free for use. So experimentally, it is very necessary to discover new two-dimensional topological insulator with very large band gap, so that they can be used at room temperature. In recent years, there are some progress along this direction. A few two-dimensional TIs were discovered. For example, single-layer tungsten telluride was found to be a 2D TI with a band gap of about 100 millieV. So quantum spin Hall effect was observed even at 100 Kelvin. So in 2019, we also observed the topological edge states in this material, the tantalum iridium telluride. So, but this is not enough. So we need.
Is this a tantalum iridium telluride for structurally is one-dimensional or two-dimensional?
This is two-dimensional. But I just want to say that this two-dimensional TI include these new materials. But today, what I would like to tell you is this new family of quasi-one-dimensional TI. So I come to the core materials today. I will introduce this new family. Actually, Professor Kondo had already tell you something about this from different technique. So my report will introduce this quantum spin Hall edge state by STM and long carrier lifetime by optical method and pressure-induced superconductivity. Then I will give a conclusion. So this material actually is very old for materials because they have been discovered in 1978, but only in recent years we rediscovered their topological materials, topological properties. The structure is like this. For the alpha phase, they have a C2 rotation symmetry. For the beta phase, they just stacked with the AA manner. So these material are one-dimensional, are quasi-one-dimensional material because this material has the basic building block of one-dimensional molecular chain. These molecular chains are packed to form single layer, and this single layer then stacked with AA mode or AB mode to form this beta phase or alpha phase. So this is basically their structure. So our calculations shows that the interlayer binding energy of bismuth bromide is only about 20 millieV, and the interchain binding energy is about 87 millieV per atom. So these numbers are very close to each other and very close to the binding energy, the interlayer binding energy in graphite and molybdenum disulfide. So this material can be very easily cleaved to form flat surface and form nanowires because they are essentially coupled by Van der Waals interaction. So by calculation, we found that the single layer bismuth bromide can be identified as a quantum spin Hall insulator. So the gap is about 0.18 eV. For few layers, if we have two layers, then the edge state will coupled with each other. Then there will have a very small band opening. So this means that the bilayer is not a topological phase. This is trivial. But for trilayer, the coupling between the three pairs of edge states still still has one pair across the band gap. So that means this trilayer is still non-trivial. Actually, if you continue to do these different signals, you will find that even even layer thick, even layer thick structure is trivial, but the odd number thick layer are non-trivial. So you can see from here. So the other very important thing is that because the interlayer coupling is very weak, so these edges on the surface are still survive from the coupling between the interlayer. So this means that if we have a surface and find some very clean edge on the surface, these edges can host topological edge states. So this means that this kind of material are very promising for future device or for future study of their topological properties. So we also calculate their topological properties under pressure. So according to theoretical calculations, the topological non-trivial phase of single-layer bismuth bromide can survive from a rather large range of strains, from -6 to 6%. So the interesting thing is that for single-layer bismuth iodide, it is near the boundary for the phase transition from quantum spin hole insulator to normal insulator. So which means if we apply some pressure on this material, it might be possible to observe the phase transition, the topological phase transition. Based on first principle calculation, the beta phase bismuth bromide and the bismuth iodide with AA stacking are weak topological insulators. But for alpha phase bismuth bromide, it is a Z2 trivial insulator. But recently, it was proposed that this material can also be a higher order TI because it is protected by CT rotation symmetry. So this means that these kind of materials are very interesting and has a lot of interesting properties. So for calculations, it shows that for this beta bismuth bromide, they are two Dirac position, the Dirac points here. But in between these two points, there is a groove structure. So this means that this structure is weak topological insulator. In 2016, this group from EPFL from Switzerland, they use ARPES to study the 001 surface of beta phase bismuth iodide. They report a prominent crossing of nearly linearly dispersed bands. So they believe that this material is a strong topological insulator from their experiments. Then Kondo's group used nano ARPES with a laser beam with a spot size of 1 micrometer. They studied the 100 plane of this bismuth iodide. They observe linear dispersion from the topological surface states, and from this 100 surface. But for comparison, they found that this 001 surface has no topological surface state. So this means that this material is kind of a weak topological TI. To explain the contradiction between the two groups, each group observed a first-order structural transition between two distinct phases in bismuth iodide at room temperature. This structural transition results in topological phase transition. By using ARPES, they identified the high temperature beta phase to be the first weak topological insulator, with two catalysts Dirac coils on the 100 surface, and have no Dirac crossing on the 001 surface. So this is consistent with the calculations. But for the low temperature alpha phase, the topological surface, the topological surface states on the 100 surface opens a gap. So this is inconsistent with the experiment, with the calculation. For bismuth bromide, Kondo's group use a laser-based ARPES to investigate their topological properties, and the overall band structure is very similar to the trivial insulator of alpha bismuth bromide, alpha bismuth iodide, but they observe a metallic in-cap state with Dirac-like dispersion inside the band gap of bismuth bromide. Therefore, the one-dimensional Dirac band should be due to the topological hinge state. So they conclude that the bismuth bromide is a higher order topological TI. So if we summarize the ARPES experimental results here for this material family, we can find that they have very different, very interesting topological properties. But this is still still need more experimental observations to find out whether alpha phase is a high order TI or a trivial TI. So what we use, the technique we use is STM. We first grow bismuth bromide on tantalum selenide substrate. We can obtain this kind of a nanowire structure. This tilted surface is the 001 surface. So on this surface, we can find some single layer step edge. We use STM measure DIDV spectral, which corresponds to the local tensor state. If the tip is far away from the edge, then we can find that there a spark gap here. The gap is about 0.1 EV. But if the tip is close to the edge, then we can find some tensor state in the gap. These states are attributed to the edge state. And if we take a DIDV spectrum at a different position along this step edge, then we find that the doses are rather similar. So the DIDV mapping also can see that they have different, they have one-dimensional feature. So this means these states are topologically protected edge states. Then we cooperate with Professor Hossain in Princeton. We use a strong magnetic field and variable temperature STM to study the quantum spin hole edge state of this bismuth bromide. We found that the bulk exhibits a very large gap here, about 200 millieV, because this is these experiments are used the single crystals, not nanowires. But if we measure the DIDV spectra at the edges, then we can find that there are some in-gap density of states here. So these edge states can be gapped by applying a magnetic field. So if the field is very strong, then we can clearly see a band gap opening here. So this means that this edge state originated from topological edge state. Then we measured the temperature dependence of this DIDV spectrum on the surface and the edge. And the spectral here the spectral here are offset for clarity. You see that at 100 Kelvin, 200 Kelvin, and 300 Kelvin, the band gap are still here. The gaps, the in-gap states are also observed even at the room temperature. So this means that the edge states are very robust against the temperature, because this room temperature, this band gap, this in-gap state can be observed at room temperature. That means this material is very helpful for room temperature device of a quantum spin Hole effect. Then we further identify the geometry hybridization of such edge states. So if for this sample, there is a single layer step edge and the bilayer step edge. We can see that there are step edge here, and there are the edge state here, and also very strong state here. These two edges. That means the bilayer can also have edge state. But if we come back to the theory, the bilayer step edge bilayer cannot have step edges. So this means this is there's something new comes. If we look at the structure of bilayer, we will find that the edge state will cover here and should cover here. But because of the edge states, but because the edge have different structure at the two ends, then we come back to the higher order TI. Then we will find that in this structure, we will see here we have a very strong hinge state, and here we don't have any significant edge state. So this picture will confirmed in experiments. We find out some position like this. There is a change here. There is a change here. So this side we have it is a bilayer step edge, and this side is also a bilayer step edge. But the structure is just like this or that. So we measured the DIDV spectral at these two positions, and we found that only at this position we have very strong density of state. This side we don't have very strong density of state. So this means that this is really a higher order topological TI. So now we see that no matter is odd number or even number SiC layer, we have hinge state or edge state. So basically, that means if we find a material, a nanowire with a lot of edge, then it should be possible to carry the current. Then use this idea, we prepared nanowires of bismuth bromide, and we measured their current carrying capacity. So our measurement of taking place in a in situ system loaded in TEM, like this. Like this, we have this electrode and this electrode directly measure voltage and the current between this nanowire. And then we found that the current carrying capacity is very high at room temperature, which is much higher than any other semiconductor, but very close to the metals such as copper and silicon and silver. So for a short conclusion of this section, I show you that robust edge states in bismuth bromide can be observed in STM by several groups, and we observe quantum spin hole edge states in bismuth bromide, and in particular with a strong magnetic field, and we observe room temperature quantum spin hole effect in this material, and also observe hinge states and confirm that this might be a topological, a higher order topological TI.
Hi, Wende, may I have a quick question? You mentioned two types of STM experiment, right?
Sorry, pardon?
You mentioned two STM experiments.
Yes.
So what was your conclusion for the first one?
The first is a very because the first experiment we don't have a variable temperature and we don't have a magnetic field, so we only observe these edge states at these step edges. So this is we can say that this is a preliminary results of the first results for this edge state. This is a very we say early stage, and but it is consistent with the with the calculations. And later on, this experiment is essentially confirmed by the second group from Hossain. They say that they observe similar, quite similar behavior, and then they applied variable temperature and the magnetic field and go further step. Yeah.
So what was the measured temperature for the first STM experiment?
Liquid helium, and we also do some liquid nitrogen temperature experiment. The results is quite similar, but we didn't present in the paper. Yeah, we have did this. And we have done this work. Yeah.
Okay, thanks.
Yeah. Okay. Let me continue. Yeah. So we have edge states. So then the lifetime would be an interesting problem. So the reason we do this work is because we are interested in the infrared absorption for infrared detector, these kind of applications. So I'm not going to say too much about this. So the material is still this kind of nanowires, exfoliated nanowires like this, or just wires, okay, one-dimensional wires. And we use infrared absorption spectroscopy and demonstrate the existence of robust topological edge states. Actually, this experiment was done very early, and maybe 3 or 4 years ago. We have done this experiment. Just to publish this paper, we spent a lot of time to do further experiments. But the main results like this: if we illuminate this material with high energy photon, then we found that the light absorption is essentially from the bulk. So you can see that the center of this nanowire has a very strong absorption of this energy of light. But if we use a low energy photo, then we found that the light absorption are essentially localized at the boundary. So this means that the boundary or the edge of the nanowire can effectively absorb a low energy photon. So this is consistent with our physical understanding of this material, because the edge state can absorb low energy photon. Then we have a look at the structure. If we use AFM to study the flat top of the nanowire, we found that the surface is rather flat. There are some steps, but not too much. So basically, you have a very wide terrace with very few terrace, very few step edges. But if you look at the side of the side surface, or we say the side of these nanowires, we can see that there are a high density of step edges. This is reasonable because we have this nanowire structure. On this surface, basically the nanowires will terminate at this position. So we can have a lot of edges like this here. So these high density of step edge will contribute to very high density of step edges, then edge states, and then this will absorb low energy photon. This is what we understand. Then because this material is essentially one-dimensional material, it's highly structurally isotopic. So if we use a polarized light, we can see the isotopic effect. This is actually what we see for higher energy. The energy of light, the light energy is larger than the band gap. Then we can see some isotopic effect, but not very clearly. But if we use a lower energy light, then this H absorption becomes very significantly reduced from this polarization parallel to the B direction or to the A direction of this nanowire. So this is consistent with the calculations. So this means that this light absorption behavior is consistent with the conclusion that this is originated from the H state. Then we use this material to we use this setup to study their lifetime. We use this infrared pump probe technique to study their carrier dynamics. It is clear that the negative signals are significantly around the boundary, but at the bulk, this is a positive signal, and the difference is that for this boundary, for the boundaries, the lifetime is very long. It's very long. It's about 1.5 nanometer, nanosecond. But for this signal from the bulk, the lifetime is very short. It's about a few tenths of picoseconds. So this is very different dynamics. So if we also have a look at different, if we use different energy density, we can see that the lifetime decrease with higher if the photo energy density increase. So this is for the boundary and also for the bulk, because if we increase the photo energy, we will have more electron-electron coupling or array coupling, because array recombination, because the hot carrier excited by the high energy density. But we can see that the long lifetime still observed for the boundary, and the short lifetime observed for the bulk. So we give a model to explain the relaxation dynamic of the photo-excited carriers. In the boundary states, the excited carriers in the helix state may relax while interlayer or intralayer scattering. In the interlayer scattering process, the back scattering by the non-magnetic disorder and the electron-phonon interaction and the direct combination of the electrons and holes requires the spin flipping, which however is incompatible with the helical nature of the boundary states, and therefore it is strongly suppressed. So the excited carriers are more likely to relax within one or two of these branches where scattering with phonons. So this scattering process suffers from a very limited scattering phase. So scattering phase space. So the relaxation time will be very long. So we have a very long lifetime of this kind of carrier. So here we listed the lifetime of observed in different topological materials, because these materials are essentially three-dimensional topological TI. So their lifetime are rather short. But for this bismuth bromide, this is essentially one-dimensional topological material. So the lifetime is very, very long. So we because this material has very interesting properties, so we prepared a bismuth bromide, best suitable absorber, and enables mode locking operation at nearly infrared bandwidth. So it may be useful for high power, ultra fast photonic device and further development of photo applications. So we have applied some pensions about in these applications. So you can see that this property is very, very nice. So in this section, I have shown you that a strong infrared absorption from the boundary states yeah. But for the bulk absorption is very weak. For the boundary absorption, it exhibits a very strong polarization anisotropy, consistent with the one-dimensional nature of the topological boundary state. So we also observed that the lifetime is very, very long. The lifetime is about a nanosecond scale. So we also use this to make some very preliminary proof of principle device for optoelectronics. So I think I still have some time to show you the pressure-induced phase transition and superconductivity. For this bismuth bromide material, we measured their transport properties, and we found that this is essentially from this resistance measurement. We found that this is a semiconductor, and we can observe weak anti-localization behavior at low temperature. This is an n-doped material, and we can observe very complicated two-dimensional SDH oscillation and weak anti-localization behavior. This behavior might be associated with the topological edge state, but at that time we cannot figure out exactly how this is linked together. Okay, we measured the transport property under pressure, and again we found that this is a semiconductor or insulator at ambient pressure. But if we apply pressure to this material, we found that the activation energy becomes smaller, and if we further increase the pressure to 3.8 gigapascal, then we found that this becomes a matter. So you can see the resistance decrease with decrease in temperature, and then it quickly drop to 0. So here is a superconductivity phase. And we also applied different kind of pressure and also magnetic field to measure the resistance. But the main idea is that to find out whether there are any other kind of superconductivity with under even higher pressure. Then we really observe a second superconductivity transition here at this at very high pressure, under very high pressure at about 9 Kelvin. At this position, the TC is about 9 Kelvin. So I'm not going to too much details here, but just show you this phase diagram. We can see that there are two superconductivity phase. This is the first phase, and this is the second phase of superconductivity. But because this structure, the crystal structure maintains in between this region, so basically it is possible to see that this material might be a Ti and also a superconductor at this region. So it means that it might be this material might be a topological superconductor. So this would be very, very interesting for future exploration. So here is the experiment. We see that under different pressure, the structure, how the structure evolved. For this pressure, it is still like the alpha phase, but for this structure, the crystal structure already changed, and at higher temperature, higher pressure, the structure is still the same, but the lattice has been pressed.
So when just make sure,
even
in the case A, it is a superconductor, right?
Yeah, under pressure. Under pressure.
Yeah, under pressure. I mean, 4.3 gigapascal.
Yeah, from the experiment, it seems that under this this high pressure, it is still a superconductor. But from the crystal point of view, it should also be a Ti, because the crystal doesn't change too much. So this means this.
You mean the lattice parameter and the beta angle? They are more or less very similar to the original ones in alpha phase at ambient pressure.
Yeah. So the lattice constant has changed a little bit, but the crystal symmetry is the same.
Okay.
Under this pressure.
Okay, thanks.
Okay, I'm not going to the detail of this. So then I should conclude for this section. So we have so there is a rich phase diagram of this material at under high pressure. So it is possible to observe two different superconductivity phase, and in particular, might be possible to observe this kind of topological superconductivity in this material. So let me give the summary. So basically, we have shown that this kind of beta phase, this kind of material, the beta phase, is a weak topological insulator. This has been confirmed by ARPES experiments. For single layer or single state, they are quantum spin Hall insulator. So we can observe quantum spin Hall states at the single steps, and this can even survive at the room temperature. And we can see that these quantum spin Hall edge states have a very great properties for infrared response and extremely long carrier lifetime. And we observe pressure-induced superconductivity phase. So it is very interesting to use this kind of material for practical application in this kind of electronic device or optoelectronic device. And I would like to thank the collaborators from this series guys. These are from Professor Yao's group, and also Professor Zhang from UT Dallas, and also experimental subgroup. These people are doing material synthesize, optical measurements, and also STM measurements. And also our collaborators from Princeton, from IOP, and from BUPT. And this work is supported by NSFC. Okay, thank you for your attention.
Okay, very nice talk. So, and we have 2 minutes for the questions. So, first question is Wang Hao. You can unmute yourself. And
yeah, I want to thank you for your nice presentation. I have several questions about the superconductivity, our Bismuth format, and high pressure. Can you go to slide 41?
This one? Maybe I should.
Yeah. Here we can see that in figure A and figure B, one is 3 gigapascal, the other one is 3.8 gigapascal. However, the resistance, there are two orders of change. Is there any reason about it?
This I have this experiment was done by Professor Xiang Li. I didn't look into I think they just focus on here, not too much of here. Maybe this is just from measurements or some reason. This they think that this is just yeah. This
okay.
I don't know the reason whether this has a second order.
Okay, can you go to the magnetic resistance of bismuth bromide? I think before or after this slide?
This
magnetic resistance. Oh yeah, this one is a figure C. Here's the MR versus B. It looks quite weird at different temperatures. Is there any reason about it?
I think the problem might be due to this edge states or various complicated Fermi surface. But I have no idea whether this two-dimensional SDH oscillation can be linked to this kind of yeah.
On your figure C, you have not seen any oscillation yet. Am I correct?
Yeah, here we see.
Yeah, that's angle dependent.
Yeah.
So on this one, particularly on figure C, you do not say any oscillation.
No, this
you do not even say signature of oscillation yet.
No oscillation. I just
so, but you do say two different type of maybe three different type of magnetic resistance behavior, right?
Right.
And they are apparently they are different from each other at different temperatures.
They might have two or three types of carrier in this material.
So you think a different carrier contribute at different temperatures?
Yeah, I think that is possible. Otherwise, it is hard to understand why this temperature dependent is so different. Yeah.
Okay. Sorry, I interrupt. Okay, sorry.
Oh, that's fine. For me, it's fine. Okay.
Yeah, any other questions?
Might have a question on the optoelectronic part. Wende actually have two questions. So one is you talk about this infrared stuff, right? So for infrared light, the wavelength is like a micron size. But however, for the edge state, according to the SEM, I mean, it is really like a 2 nanometer, so which is way smaller than the wavelength of the infrared light. So therefore, how can you claim the signature coming from the edge?
This is very interesting. Actually, we have to fight against the reviewers for a long time because of this problem. Basically, it's like this. If the same photo, if you illuminate at this position, then you have one absorption intensity, and if you focus on this side, then you have another intensity. In principle, you will see that okay, here, if the structure are the same, then here and here should be the same, but actually here is stronger.
But that is not edge, that is side. That is side surface.
Yeah, basically, if you experimentally, if you prepare a wire, you have a top surface and the side surface. But on the top surface, you have very few edges. But on the side surface, you have a bunch of, you have a lot of edges. And the only difference here and here is the top and the side is only the density of edges. So that means you have a direct link between these.
I see, but now I understand you mean, what do you mean by the edge? But that edge is kind of like a collection of many multi-layer edges.
Yes, exactly.
So some of them are even layers, some of them are odd layers, but the even layer ones they actually
They
have very
have,
complicated.
high,
Sometimes they don't have edge states.
But basically it's like this. If you have odd number of the layer is odd number in thickness, then you have edge state. But if you have an even number, then you have hinge state, or you have this kind of slightly gapped edge state. This edge state, or surface state, that's fine. I mean, basically, the origination is from the edge state, the topological edge state. But if it's even thickness, even layer thickness, then they have a very the edge state, the surface state has a very few gap. I mean, the gap is only about 20 millieV.
Yeah, therefore, for infrared light, the transition
fine.
is actually for the surface state, right?
So basically here you have because in the original version of my paper, I say this is a topologically originated edge state. So for this surface state is originated from topological edge state, but we cannot say that this is edge state for even number the thickness.
The thing, sorry, Fan. The thing is, how can you tell this is you have a kind of like a multiple edge like this? It's not a clear cut as a 100, basically that surface.
No, we don't need that kind of a surface. This is give us a statistical analysis. We just have a bunch of edges, different type of edges. No matter its thickness is 1, 2, 3, or 5, or whatever. But for any type of these edges, they should have edge states or hinge states. This edge state or hinge state, no matter it's trivial or non-trivial, they should have response to the optic for the infrared. They should absorb some infrared. Then these will give us very strong infrared absorption at this position. So basically,
there will be some contribution from the edge state in your definition. However, there should be more contribution from the surface state.
This is only basically for exploration. You should have a equal possibility to get odd number thickness layer. Or
I understand. If you think about it, if you have a kind of like let's say you have a few layer domain which is flat, right? And in that domain, at most you contribute 2 hinge states or 2 edge states at most. But however, you have more than 2 layers which contribute to the side surface state. So which will also have very strong infrared response.
So if you carefully look into this, I mean, you can say that these are boundary states. Basically, you can say that these are boundary states.
Yeah, boundary states, right?
Boundary state should be better. But I would say that these boundary states are originated from the edge state of single layer. They are just coupled from that.
I agree with you that's true. Yeah.
Can I, since you're on this slide, Fan, you might have more questions. Let me just ask a naive question here. If I understand you correctly, you are talking about this one as nanowire, but I see your scale bar is in micrometer.
Yeah, because the thickness is not in nanometer scale. So
so it's not a really nanowire in terms of the width.
The length is in micrometer scale, but for the thickness is nanometer scale. The width is also a few hundred nanometer scale, or even it can be as narrow as a few 100 nanometer, but it can also be much wider than micrometer. Yeah.
Okay.
So this depends on how you do this experiment. It can be very thick or very narrow.
But now the dimension you draw is actually width and the length, right?
Yeah, here this is along this direction is
That's
length.
your chain direction. Am I
Yeah,
correct?
and then this direction is width. Along here, from if you look at here, this is thickness. So this is a three-dimensional plot.
Okay, maybe let's move to the next speaker.
Yeah, thank you.
Thank you, Professor Xiao, for a nice talk. So the next speaker